and humidity indicator. Now, there are many ways to measure temperature and humidity. There are many different devices that will do this for you. But generally, they require you to be near the point of measurement. They require you to read an analog or digital display. My paper design has come up with a unique way of displaying that information. It will actually take and display the information on a television set when a button is pressed, much in the same way that when you press your remote control on the television set when you're operating the VCR, it displays the channel on the screen for a couple of seconds. If you look at the block diagram, we'll start over here. We have the temperature and humidity transducer. That's fed into a Motorola evaluation board based on the MC68HC11. We have CPU for computations. We have RAM, ROM to store our firmware and data. And we have I/O. And the I/O's purpose is to detect when a button press has been made, and to output on port B the character information once we've taken the measurement and determined what the appropriate numbers to display on the screen are. We also have an RS-232 input for development capability. Now, the key to this circuit is the actual video generation circuitry. And to start with, we need a video source, such as a VCR, to position the characters and ensure they are in the correct proportion and displayed in the right place on the screen where we decide. We need some sync separation circuitry, and I'll talk more about television syncs later. We have a video line counter circuitry to count the synchronization pulses so that we know where on the screen we are. And then we have character generation and a video interface. And there we have an analog switch to switch between standard video and my locally generated video. And that's fed to a video amplifier and to your television set. I'd like to start the detailed discussion with the temperature sensor. The temperature sensing element is a National Semiconductor LM35D. It outputs 10 millivolts per degree C. It has a linear output. It makes it very convenient for use in microprocessor projects. The output of that, I should say that this is not co-located with this circuitry. It's on the end of a probe, and I'll show you that later. The output of the LM35 is fed to a buffer and op-amp. I have a capacitor here to filter out any noise that may be generated in the probe wires. And then to the scaling amplifier. And the purpose of the scaling amplifier is to it'll have a gain of 5 to ensure that when we have 1 volt output for 100 degrees C, which is the operating limit of the LM35D, that will correspond to 5 volts input to the A to D converter on the HC11, which is the operating range that that device is spec for. We also want to display humidity. To measure humidity, the heart of this is the humidity sensor. This is a variable capacitor, and it's made by Philips Components. And the operation of this device is fairly simple. There's a sheet of mylar, and it's sandwiched between 2 thin films of gold foil. As the humidity increases, the capacitance of this device increases. Now we can use that to generate a voltage by having a stable reference oscillator. This operates about 10 kilohertz. The second oscillator also runs at 10 kilohertz, but its duty cycle is a function of the humidity. I should say that this stable reference is set initially for 50% duty cycle. The outputs are fed to some NOR gates, and their outputs of these NOR gates, there's a pulse width difference, and it's rectified, and that's converted into DC voltage. Give you an idea of what the timing might look like. We have our stable reference, the variable pulse width out of the humidity sensor, and the output is the difference in the 2 pulses, and this is what's fed to the rectifier circuit. Now let's get into the video section. And to understand that, you need to understand a little bit about video, so let me talk about that quickly. Video works on the principle of scanned lines known as raster. The start of a scanned line is called horizontal blanking pulse. And this is what we have to count to know where on the screen we are and to position the characters. After horizontal blanking pulse, we have a color burst, which is used in color television as a reference, a phase reference, so that the colors you see on your television are reproduced accurately. The last 52.4 microseconds of an NTSC standard video, which is what our American television runs on, contains all the actual picture information in an analog format. Now this is what the display concept is. And I've blown these two letters up. They're much bigger than they would be, but this is for the purpose of our demonstration. You see here, once we detect line 128, we'll begin to start our display. And each character is built up with a series of 8 dots across, 7 dots down. And each dot is actually built up in thickness of 7 lines. So that means that we have to enable our video circuitry for 42 scan lines. I have a block diagram of the video circuitry. We have sync separation. We have to be able to control the characters. We have the character selection. We have the video character stored in RAM, that's output from the EDB. We have a dot pattern stored in EEPROM. We have a shift register to shift the information out in serial format. Now let's look at a couple schematics. The sync separation is accomplished by this LM1881 from National Semiconductor. The purpose of this IC is exactly what I needed. It separates the sync pulses out and presents them on separate pins in a TTL compatible format. Now I can take these sync pulses and I should say the vertical out, it will be the start. The vertical tells the television set to start up in the corner and begin scanning. And that'll be like a 0 trigger. Once that starts, we start counting horizontal syncs. We have U15, U16 there are cascaded together to detect line 128. Once line 128 is detected, we have these two counters, U17 and 18, to detect, to open a gate of 42 scan lines, which is the exact amount I need to display the characters. During the 42 lines, this analog switch here switches over from the externally input video to my locally generated video. Now we can look at the video character generation circuitry. We have a parallel port to output from the RAM the characters I want to display. U9 here is a one-shot, and I've configured that to do a little memory write cycle to pull the RAM low so that it can be written to. That's controlled, that one shot is stimulated by the strobe D off the controller card. And I have RAM, as I said before, to store the characters I want. The RAM will select in the EEPROM the character I want, which has the dot pattern I need. And then U4 is a shift register that will shift the parallel output of the EEPROM to the analog interface. The counters here along the bottom area will control which character is selected, when the character proceeds to the next one, and how many lines there are. When we go back to this circuit, the output of that shift register comes over here to right there. And I have built up a voltage divider network which works in conjunction with the horizontal sync pulses. That will allow us to generate in analog format the correct output for the characters. So I'm converting from a digital output to an NTSC compatible analog output. This information is fed to the HA5190. It's a video op amp. This op amp is only stable for a gain of 5. And what I've done is I've set the op amp for a gain of 5. And then I have a voltage divider on the output, which will make the effective gain of the network 1, with an output impedance of 75 ohms, which is the standard for NTSC compatible coaxial transmission. My assistant will come and join me. I'd like to show you the project now. something I got at work. I've been a technician at a place in El Monte for about 10 years now, and they have a big scrap heap, so almost everything you see here is recycled material. This probe comes from a desoldering station, and I looked at it and I noticed it had a momentary switch on it, and I just took the guts out, and it houses the sensors nicely. And you can actually get air through there, and probably get the best results if you wave this one across to move some air through there. We hold the circuitry up. Here's the controller card. This is something that's made by Motorola. DC power supply, which is connected to the wall, and I have a fuse. We need for this circuit 5 volts, plus and minus 12 volts. This card contains the analog interface circuitry. This strip here is basically the temperature transducer, and this is the humidity transducer circuitry. Let me move this card. This is the video card. This is mostly the analog side. You can notice I knew my video would come in on this side, so I had all the analog basically on this side nearest to the coax, so I can keep that as short as possible. And this is what interfaces to the 60-pin connector on the EDB. And this is the EEPROM that will store the character data. I put that on the header so I can remove it. And when I'm finished, I'll be able to plop it right back in here and it'll run standalone. This is basically the character generation side, and this is the line counter and analog gate opener circuitry. And I'd like to conclude by saying that this has been a very hard project for me, but I've learned quite a bit.